Alright, Logic fans, welcome to our second video on 3.6. This is video 3.6b, and we're continuing our discussion of conditional proof. Now, one question I get a lot, and you're going to get this we're going to keep going through these examples, okay? And of course you need to practice the problems, but the one question I get a lot is, Ash, can I only use conditional proof if the conclusion of the argument I'm investigating is a conditional? And the answer to that question is no. You can kind of cheat a little bit. This is really interesting, okay? So you can get a little bit creative with this. Here's a question for you before we start syntactically deducing this conclusion from these premises. If this conclusion, which is not a conditional, were to be transformed into a conditional, what conditional would it look like? And how would you get that conclusion to that conditional? Okay, so hopefully some of you have sort of figured this out, but, right, not A or B just becomes if A, then B, right? By what rule is that, right? That's impla, okay? So we can kind of picture in our mind's eye this conclusion as really looking like this. Of course, we've got to get it to this form. That's the form of the argument. But in our mind's eye, we can sort of picture the conclusion this way. So given that, what would my assumption be in this particular case? Okay, hopefully you're able to get it, but it's the same thing you're always looking at. It's the antecedent of the conditional that you're looking for, and this is kind of the conditional we're looking for now. So we're going to write 2a, that's what we're assuming, and now that we've assumed that, what are we looking for? Well, we're looking for the consequent, which in this case is b. So what we're going to do is we're going to show this conditional, and then we're going to convert it to this using impla, okay? So what I want you to do now is take a second and see if you can use this assumption and this premise to get B all by itself. And once you do get B all by itself, stop there. So pause now and try that. Okay, hopefully you were able to get it, all right? But look, I mean, modus ponens on 1 and 2 yields this, B and C, right? So that's modus ponens on 1 and 2. We're trying to get B all by itself. Always keep, this is why I make you write it down here. What am I trying to get? So you're focused on that, right? B, simp, and it's fairly straightforward in this case, but I'm just trying to illustrate the method to you, okay? So that's going to be simp on 3. And now, having obtained what we wanted, okay, here's B, that's what we were looking for. We've got it. There it is. What do? We discharge the assumption. So we're going to get line 5 here. We're retracting our assumption, and we're going to get the first thing we wrote down, which is this guy. We're going to get arrow, the last thing we got, which is, in this case, this guy. Okay? And so you're going to justify that by writing CP and what? 2 through 4. Okay? Very good. And are we done yet? No, because we're supposed to syntactically deduce this. So how do I get from what I've got here to this guy? Pause now. Okay, we're just going to use the same thing we did to get from this to our make-believe conditional here, which was impla. Okay, so this is going to be impla on 5, and that is QED. All right, that is absolutely QED. All right, and that is a demonstration of syntactic validity of this argument, which uses conditional proof. Now, I want to stop and take a second. So you might have thought, hey, Ash, I think I can figure out how to get from the premise to this conclusion without CP. That's absolutely fine. It's totally fine. But that you will find, okay, that the use of CP does make a lot of arguments a lot simpler. So it's actually a general truth. We don't prove it, but it's just information for you. It's a general truth that whatever can be proved using CP can be proved without CP using our other syntactic rules. So in that sense, there's a sense in which conditional proof is unnecessary. But CP, you will find, does make a lot of proofs a lot more straightforward and a lot less cumbersome once you know it. Okay, once you're familiar with it and you've practiced it and you're comfortable with it, you will actually find CP to be a very natural way to reason, and it is historically a natural way that you find mathematicians and logicians and philosophers and other scientists sort of reasoning. And so it is a really good one to learn because it is such a natural way of arguing. And again, it might not be natural to you at first, but once you've got the ins and outs of this down, CP 2 through 4 and how to do it and all that, you will find that it lines up with a natural way of thinking very readily. Okay, something else I want to warn you about. Some students do this, right? So let's suppose we've gotten to, like, I don't know, somewhere around here. Maybe a student looks at it and says, okay, I'm trying to get not A or B. And so I've got B here, but now I can just sort of do B or not A. And that, of course, would be add on 4. And then they'll sort of go, okay, I'm looking for not A or B. And so I can just sort of get that by doing not A or B. Okay, and that's comm on 5. Now, there's nothing wrong with what you've done here in terms of your application of the rules. There is something wrong, though, namely that this whole thing here, this does not count as a syntactic deduction for us, okay? This is not a syntactic deduction. And it's not a syntactic deduction for us because it has an undischarged assumption. Every syntactic deduction has, if it has any assumptions, every one of those assumptions is discharged. It must be discharged, meaning you got to move back here, and that means that you would end up writing something like 7, if A, then A or not B. So you would end up writing down the first thing you assumed, right, which was this thing, arrow, the last thing you got, okay? And notice how this ends up working out, all right? So you would end up with that, and that would be CP 2 through 6. And the idea here is that, look, this now is a syntactic deduction. It doesn't have any undischarged assumptions. All of its assumptions have been properly discharged. The problem, though, is that this is not this here, which the syntax forces you to write. It forces you to write the first thing you did, arrow, the last thing you did, okay, is not this. All right, 7, line 7, this string here is not this string at all, okay? So this is a syntactic deduction. It's properly discharged all of its assumptions. The issue is that it's not the string that we're looking for. So be aware of that, okay? Some students will try to sort of go to this and they'll say, oh, I'm done. And I'll say, no, you haven't properly understood conditional proof. You have to discharge your assumptions, okay? You can't just have, I made an assumption and then stopped. It's like, okay, what followed from that assumption? And what you've actually shown is your assumption arrow, the thing that followed from it. In this case, A arrow, if A arrow, not A or B. Okay, so this does not count. Don't do that. Do it the way we did it, which was the proper way. Okay, so on this theme of, the conclusion you're looking for does not have to be an actual conditional. Like in the last one, it was a disjunction, but we converted it to a conditional and made assumptions that way. That theme is probably most often exploited when the conclusion you're looking for is a biconditional. Okay, so in this case we want a biconditional, and we often use CP to demonstrate biconditionals. This is a very common, well-trodden way of showing a biconditional. So let's have a look at how it works. So here's the argument we're supposed to use CP to demonstrate is syntactically valid. You might try to give it a shot without using CP. You'll find it's rather difficult, but it can be done. So first question for you, though, since we are going to use CP, what does this look like as a conditional? Pause now. Okay, well, as a conditional, right, a biconditional is just two conditionals. So in this case, you've got your left to right direction if A then B, and your right to left direction if B then A, okay? So this is really just two disguised conditionals. So what we're going to do is we're going to use CP twice. First, we're going to use CP to prove the left to right direction. We're going to close that off, and we're going to have our left to right direction. Then we're going to use CP a second time, and we're going to get our right to left direction. Then we're going to use conjunction to conjoin those together to get this sentence, and then we'll use equiv to get back to this form, okay? So here's what we're going to do as I walk you through this, all right? First thing we want to do is we're going to prove this conditional all by itself. What's the antecedent, what's my assumption, and what am I looking for when it comes to this conditional right here? Pause now. Okay, hopefully you've got it, but your assumption is A, okay, and you're going to write assump, and what you're looking for in this case is just B, all right? So I'm just thinking about this conditional right here. Now what I want you to do is use 1 and 2, okay, and then what I want you to do is I want you to try to find B. Pause now. All right, so there are different ways of doing this. Here's the way I'm going to do it, but this is going to be double negation on 3, and that's going to set up disjunctive syllogism on 2 and 4, okay? And now that I've obtained B, what I was looking for, I discharge my initial assumption, right? So I write down the first thing I assumed, which was this, okay? And then I write down arrow. So let's get my arrow in here. And then I write the last thing that I got, which was this, okay? And then what I do is I justify that by writing CP 3 through 5 in this case, okay? So that's exactly how that works. Now, what I've shown so far from these premises is if A, then B. I want to now show if B, then A. So what's my assumption going to be in this case, and what am I going to be looking for? Okay, my assumption in this case is the antecedent, which is B. Okay, and I'm going to write assump, and what I'm looking for this time is A. Okay, so now what I'm going to do is I'm going to use what I have available to find A. What do I have available? I've got my assumption, I've got this, and I've got this. These are not available. We haven't shown these. These were things that held if an assumption is made, okay? And so those are not available. Anything that's inside of here is not available now, okay? What is available is your assumption and any other lines that you've absolutely demonstrated, okay? So 1, 2, 6, and 7. Using those, find A. Pause now. Well, it's a little bit awkward in this case. I've already got A up here, but the thing is I need it below my B assumption here so that I can discharge it and get my if B then A. So in order to get this guy down here, I just use this little trick, okay, where I go like this, and it's just a really simple sort of thing, all right? So I'm just going to say double negation on 1. I'm going to do double negation on 8, okay? And now I've got my A below here, and so having found what I was looking for here, I can discharge my assumption, and here what I end up getting is the first thing I assumed, arrow, the last thing I got, which in this case was A, okay? And that's going to be CP on 7 through 9, okay? All right, now comes the real sort of trick here. What we do is we build this guy, right? So we're going to build him like this, and that's just going to be conjunction on 6 and 10, okay? So that's conjunction on 6 and 10. And now, can you finish it from there? Can you get from this thing to the desired guy, which was this guy? Pause now. Okay, hopefully you're able to do it, but that's just a equiv on 11, okay? And once again, this is a very common way of how you prove biconditionals. You think about it in terms of two conditionals, you prove each conditional separately, then you can join them together and you equiv to your biconditional. Okay, more practice to come on the third video. Look for 3.6c. See you there.